To solve this equation, we're going to go through and take our candidate solution, which is our y of t equals e to the rt, and take its first and second derivative and substitute them into the original differential equation. So y prime of t is r times e to the rt, and our y double prime of t is r squared e to the rt. We now substitute those into the equation, and you will see that we've got an r squared e to the rt minus 2r e to the rt minus 15 e to the rt equals 0. We can now factor out the e to the rt. Leaves us with r squared minus 2r minus 15 is equal to 0. And we know that exponential functions are never equal to 0, so we can divide both sides by them. And that takes us down to just r squared minus 2r minus 15 is equal to 0. And this equation is called the characteristic equation, and it's also called the auxiliary equation. Our textbook likes to use the word auxiliary, but the Polking textbook likes using characteristic. So it's up to you, whatever you want to call it, but it is a very important equation. And for second order, it always yields a quadratic equation. Oftentimes you can factor them. This is going to be an r minus 5 times an r plus 3. That's equal to 0, giving the two r values of positive 5 and a second value, which is negative 3. It should be noted that these two numbers here are distinct and they are real. So therefore, we're going to have the simple exponential case for our general solution. So our solution of our problem is going to be y of t equals arbitrary constant c1 times e to the 5t plus second arbitrary constant c2 e to the negative 3t. And again, we can actually verify that this is a solution by going through and taking the first and second derivative and showing that it makes the original differential equation a true statement. And again, this is the case when you have two distinct real numbers from your auxiliary equation.